I looked at everybody's homework that was turned in by the time I stopped reading email late this morning, and it was all perfect. So good luck for the rest of you getting it done by midnight. I will have office hours at 4 o'clock today if you have any problems. One thing I said by an announcement that should have generated you email is that I had sort of assumed when I sent the email that it's fine if you just add the recursive specular reflection. I had assumed that they had done ray triangle intersection as part of that package, and they hadn't. And I do want you to implement some form of ray polygon intersection, either the version I handed out in those sheets or the version that I talked about in class using those dot products with the plane equations for a convex polygon, which would work for other convex polygons besides triangles. Either one is fine, but I do want your scenes in the future to contain polygonal objects, and you get the ray polygon intersection. So that's something you can even start working on now, even though I haven't covered the lecture material for the second assignment yet. So in order to get to that stuff, I want to continue with random variables and statistics. I hope people benefited from the lecture last Friday, in favor of which I canceled this class. But it may be 2 classes before I catch up, but I'm sort of at least halfway through this material already from last week. So we're going to look at x and y be 2 random variables and actually I want them to be independent, where I wrote the definition of independent on the board last Wednesday, and I'll use it in the middle of this, so I'll be repeating it. And what we want to look at is the variance. I'm being a little more general than I was planning to last time, looking at a function of a random variable. Actually, a function of a random variable is just another random variable. But we'll keep this notation because lots of times we'll be using functions of variables. The variance of the sum of 2 random variables or 2 functions of 2 different random variables. By definition, that's the expectation of fx plus gx. Actually, not by definition. By the property I proved last time, we can write it as the expectation of this thing squared minus the square of the expectations, fx plus g of y. Do the expectation first and then square it, right? Because we proved that the definition had, a minus 2 times something that canceled the plus 1 something squared, and it ended up being this. Okay, so now we can write this as the expectation. I'm just going to multiply this out. F of x squared plus twice f of x g of y plus g of y squared. And for here, what can I do? For here, what I can say is, I already proved last time, if you have the sum of 2 random variables, whether they're independent or not, the expectation just comes out because it's really just a sum. So it's expectation of f of x plus the expectation of g of y squared. And I'm subtracting that. So I'll end up multiplying this out. But now I have the expectation of a sum of a bunch of different terms. And, they're all functions of random variables. So, if y and x are over a different experiment state, then we're really going to have the cross product of the events in both experiments, and their sum is maybe a double sum, but the principle is still the same. So for this, I have a sum of expectation. Let's see, my squared here If I put g of y squared, let's make it look like that. So I can say this is the expectation of f of x squared. Let me forget the extra parentheses. You know I'm squaring f of x. Plus twice the expectation of f of x g of y plus the expectation of g of y squared. And now this thing squared, I'm going to have minus the expectation of f of x. Let's see. I think my square is in the wrong place, right? I'm supposed to have the sum of these expectations and square them. So I have to take this expectation and square it, plus twice the expectation of f of x times the expectation of g of y. Let's see. If I have minus on all of these, this should be minus 2, and I should be subtracting twice the expectation of g of y squared. So I'm sort of close to the answer. I need a bunch of equal signs here. And if this term could cancel with this term, then I'd be okay, right? Because this term minus this term is the variance of f of x. And this term minus, there's no 2 there. This term is the variance of g of y. But what I'm left with is twice the expectation of the product minus the product of the expectations. So the question is the expectation of the product the same as the product of the expectations? And this is the point at which I need to use the fact that they're independent. If they were correlated, then this would be a measure of the correlation. So what I want to do is compute this expectation and somehow relate it to, let's see, this is the expectation of the product, and this is supposed to be the product of the expectations. This term. Somebody didn't correct my algebra mistake. F of x e g of y. Right, that's from this term times that term, and I left off some parentheses there. Right, so the question is the expectation of the product the same as the product of the expectations? And that's going to be true because x and y are independent. So if I look at this expectation of the product, you know, one way to write it is it's the double sum over all x and all y of f of x, g of y, times the probability of x and y. Another way to write it is to say it's the sum over all values r that x can take and all values s that y can take of f of x, g of y, times the probability that x equals the value r and y equals the value s. And what I gave as a definition of independence last time says that, let me write this first part and then get back to that, f of x, g of y, that this is the same as the product of the probabilities x equals, that x equals r and the probability that y equals s. That's sort of another way of saying this probability is the same as the probability for x times the probability for y. This is just a fancy way of writing it when you think of specific values. So that's what it means to be independent. If you do both experiments, then after you've done the first experiment with probability x, and then you do the other experiment, the answer you get after you do both of them is really just the product that the first one will come out and then the second one come out to whatever this value is. It doesn't, in other words, after the second experiment doesn't depend on the first experiment. That's really what this is saying. It may be clearer this way, which is why I write it this way. Okay, so now we can basically use the distributive law, right? Because this is a big sum over S, values in S, but they're only concerning y. So these things are constants, multiplying all the terms in this inner sum, and we can take them out of the inner sum and write it as the sum over R of f of x, the probability x equals R, times the sum over S of g of y times the probability that y equals S. Right, so this is a big sum of a constant times a bunch of terms. So the sum is really just that constant times this, right, because I factored this out. So this is the expectation of f of x, and this one is the expectation of g of y. So, but to prove that the expectation of the product is the product of the expectations, I really needed this independence. It's not true in general. I think I gave you an example last time where they're not independent and everything comes out wrong. Okay, so this was all for discrete variables. But now I want to talk about continuous variables. Because what we're going to be sampling is, say, a set of directions or a set of instants of time for motion blur or something. And that's a continuous variable. So I'll write it as if it was only one continuous variable. But like directions, if you represented directions on the sphere with a polar angle and an azimuthal angle, that would actually depend on two parameters. I just don't want to write multiple integrals here. So what we're going to do is talk about, say, probability on a line. And I think I said sometime in this course that the chance of getting a specific point on the line may be 0. What you're really interested in is an integral over, say, an interval of the line. Or if it were 2D, say a 2D dartboard, you know, where you have these circles and you're throwing darts and your experiment is only if the thing actually hits the board. I guess actually most dartboards are round. They hang them up on the wall as a round thing, or, you know, a target, right? Really, it's x and y. And so if you make any region, like this inner circle, you can ask, what's the probability of hitting the inner circle? The probability of hitting the actual inner point is 0, except in movies where they cook it that way. Like when I remember when I was a kid, I saw Robin Hood split his own arrow to get in the center twice or something. But really, it's an integral over an area that gives you a finite probability. It's a probability density, right? So if we have a region, say, from A to B, we can say the probability that A is less than or equal to X is less than or equal to B. That means that our sample is in this interval is really the integral from A to B. Maybe I should use probability for here and lowercase p for the probability density. So maybe this should have said probability. Is the probability density of x, or maybe I'll use r, of given value dr. So basically, the probability is now a density function for every value r in the line or for every 2D point in the plane or whatever. it's a non-negative density, and instead of summing to 1, we're going to say the integral over the whole line, or double integral over the whole plane of P of R dr equals 1. In other words, if you integrate this density for all possible values, you're going to end up 1. That's equivalent to saying for the finite case, the probability of all the finite events, if you add up that finite sum, you get 1. And another thing that's useful is the cumulative distribution function. Did somebody have a question, or you're just coughing? So I'll say CDF. CDF of some number b is the integral from minus infinity to b of the probability of R dr. And the usefulness of that is if you have that one cumulative distribution function, then you can have the probability that x is between a and b as just the difference of this indefinite integral from b, cumulative distribution function of b, minus the cumulative distribution function of a. Well, once we have this continuous variable, we can still talk about expectation. The expectation of a random variable, or I could have stuck a function in here too, is the integral from minus infinity to infinity of x times the probability density of x dx. Right? It's sort of weighted mean of the function x weighted by the probability. And it makes sense that it's a weighted mean because the integral of all these probabilities add up to 1. So it's just, this is the continuous variable analog of the definition I gave for expectation as a sum. Let me just ask, how many people is this kind of stuff already familiar? About half. Okay, so it's going to be easy for you and maybe hard for the people who are seeing it for the first time. So the same thing for f of x. E of f of x, it's just this integral from minus infinity to infinity of, instead of fx, I'll just put f of x, p of x, dx. So that's the expected value of this continuous function of this continuous variable. And similarly, we can have the variance of, let's see, I just wrote it x instead of f of x in my notes, which the book calls sigma squared, and that equals the expectation of x minus its mean. This expected value you can think of as the mean. So for the purpose of this expectation integral, this thing is a constant. And so just for an exercise, I'm going to show that this formula I used for the variance on the left-hand board in terms of a difference of two quantities, the same proof that I proved that for the discrete case works for the continuous case, just to show you basically everything we did for the discrete case worked. So, and I missed a square here, didn't I? Typo. It's the expectation of the squared difference from the mean. Root mean square, basically, is the sigma, which is the standard deviation, if you took the square root of both sides. So this is the integral from minus infinity to infinity of this particular function of x, which is x minus e of x squared times the probability of x dx. And now I'm going to multiply out what's under there. X squared minus, and this could have been a function too if I wanted. Twice x e of x plus e of x squared times p of x dx. Okay, so I've got three terms here. And so maybe I'll make three integrals. The integral from minus infinity to infinity of x squared p of x dx minus twice. And from this, I'm going to factor out the constant e of x. So just like the distributive law for a finite sum, when you take a constant out from under an integral of a constant times the function is that constant times the integral of the function. It's a sort of a continuous version of the distributive law. So twice e of x, that constant times the integral from minus infinity to infinity of x times p of x dx plus the integral from minus infinity. Well, actually, I could take a constant out of that one too. E of x squared is a constant for this. I'm implicitly multiplying each of these terms by p of x, doing two steps in one. So now I can take this constant out, e of x squared p of x. Let's see, then out of the integral, and then I have the integral from minus infinity to infinity of p of x dx. And I know this is 1 because that's what a property for probability density. So this term is just e of x squared. This factor is e of x by definition. So this term is minus 2 e of x times e of x, which is an e of x squared. And this term is, here we have the integral of this function of x times p of x dx. That's the expectation of that function of x. So again, we have two of these terms with a minus sign and one with a plus term. So the answer is e of x squared minus the expectation of x squared. So it's basically the same proof. I'm factoring constants out of integrals instead of applying the distributive law to finite sums. Okay, so let's see. What did I want to do next? So I guess I want to show you that e of two functions. Did I write it f and g? No, I did. Yeah. E of, maybe I should start it on this board, though. Start from the beginning. If I have two continuous random variables or two functions of continuous random variables, I want to show that e of f of x plus g of y is the sum of the expectations. E of f of x plus e of g of y. So it's a little different. I think last time I had functions of the same variable. Now I'm talking about functions of two variables. So in addition to changing the situation to talk about continuous variables, I'm also using two different random variables. And my claim is I can prove this fact whether or not these are independent or not. I don't need the independence to get this fact. I'm only going to need it to get the variances equal to the sum of the variances. So really, if you think about these are two independent variables, then this is a function of the two independent variables, and this expectation really means the integral from minus infinity to infinity for both of them. F of x plus g of y. And the probability of both of them. Okay, so what I want to do is try and get this as the sum of two integrals, and then factor terms out of the integral. So the first one is a double integral of just the f of x, P of x, y, dx, dy. And the second one is the double integral of just the gy term, P of x, y, dx, dy. Right? So now this probability depends on both x and y, and I'm not assuming they're independent, so I can't write it as a product. But I can still do something with this term, namely this f of x can be, let's write it like this, dy dx. An outer integral over x times an inner integral over y. And in that inner integral, this function of x is a constant independent of y, so I can take it out of the integral. And so I'll write this as the integral from minus infinity to infinity of f of x times the integral from minus infinity to infinity of p of x, y, dy. And I guess before I try and do the next step, why don't I do the same thing here? Integral from minus infinity to infinity. Now I can factor out that g of y is independent of this integral over x. So I'm just doing the same thing. Integral from minus infinity to infinity of p of x, y. And now the inner integral is over dx. And the outer one, here the outer integral it was over dx, and here the outer integral is over dy. So let me go over two boards to my dartboard example, where suppose you had a probability. Probably for a dartboard, the probability really depends only on the distance from the center. But you know, some people might tend to the right more than to the left, or they may be more accurate in the horizontal dimension than the vertical dimension. Whatever it is, it's a 2D distribution. If we only cared about the x-coordinate, what we could do is we could think of, here's this probability density. Maybe it's brighter where the things are higher. It's the only way I can draw it, because in 3D I'd have to draw a mountain here. And imagine projecting all this density down. So for each value of x, we add up an integral over all the y's. Then we get a probability that depends on x. And so this probability is called the marginal distribution of the two-dimensional distribution. It's the integral from minus infinity to infinity d of p of xy, the density along this vertical line, dy. Right, so from the two-dimensional density, we can get a one-dimensional density, which says, forgetting about what happened in the second experiment, say, I drew it as if one dart throw, but you could also think of it as two experiments where maybe the value of the first experiment somehow influenced the value of the second one, as it does in quantum mechanics, even though they're two separate experiments. So this is really just the probability of x when you don't care about what the y measurement was. And similarly, we can have the marginal distribution along the y-axis for some value of y. We can find the marginal distribution of y as the integral along the whole horizontal line of p of x dx at this value y. P of xy, I'm sorry. Okay, so if I go back to this board then, this thing is that first marginal distribution p of x, which you could think of really as the meaning of p of x, or p of y, for this distribution of both x and y where it doesn't have to be independent. We can still think of the probability of x not caring about y and the probability of y not caring about x. And so this integral then becomes the expectation of f of x, and this integral becomes the expectation of f of y. So I really didn't use the fact they were independent. And we could have this double sum instead of this double integral, even for the discrete case. And I could prove similarly with these marginal distributions that even if these are different random variables, this rule still holds, whether they're independent or not. Okay, so let's see. What else do I need to talk about here? We're going to look at the average now. We're going to use the facts that we had. I guess, I'm not going to prove it, but if x and y are independent, then the variance of f of x plus g of y equals the variance of f of x times the variance of g of y. And the same definition, independent means p of x and y together equals the probability of p of x times the probability of p of y. And then, just like I had sums at the beginning of the period, you'd have integrals. And you'd be factoring out and doing the same sort of proof. So I don't think I want to repeat that one for the continuous case. And I'm missing a plus sign, not the product. I'm adding these. Okay, so now let's look at a collection of independent, identically distributed random variables or functions. So I'm going to assume x1, x2, I think the book uses a capital N, are n independent. I guess if I'm going to be consistent, I'm going to have trouble making my n's capital all the time. N independent random variables. And I guess for what I'm going to do, I should mention that once you have two, you can prove more by induction. Either variances when they're pairwise independent, or sums, whether or not they're independent, just by mathematical induction. So I'm really going to be using for multiple different f, g, h, and so on. So in this case, this could really be a case, and that's what we're going to apply it to, of repeating the same experiment over and over again. So, but each value you get is different, right? So, if I flip a coin 10 times, that's 10 different experiments. Or if I throw a dart 10 times, that's more like it because that's continuous variables. So for continuous variables, if I have n of them, that means the probability of getting the first one to be x1, the second one to be x2, up to xn, is the product of the probabilities times the probability of x2, probability of xn. Although I think to prove this, when I expand the square, I've only got two products at a time. I have a bunch of cross terms, so I probably only need them to be pairwise independent. So as I said, an example would be repeated independent trials of the same experiment. And so let g of x be a function of x. And we want to look at the average value that we get, say, from these n experiments. And so what I'll do is I'll just, sometimes for shorthand, I'll use a capital X for all of these variables taken together. x1 up to xn, this n tuple of outcomes for all of them is capital X. And so g of capital X is really g of this x1 up to xn. And it's just the average. 1 over n times the sum from j equals 1 to n of g evaluated at the outcome of each of the experiments, which is the xj for all these things. So you're going to like flip a coin 100 times and count 1 if it's heads and 0 if it's tails. And then you're going to take the average of those numbers. And it should come about close to a half, I guess, if it's a fair coin. That's the sort of thing we're doing. But it will eventually apply it to computing integrals, although I may not have time to do that today. I hope I will. Then the expectation of this average is the expectation of 1 over n times the sum j equals 1 to n g of xj. Now, one thing I didn't show is the expectation of a constant times a function. Is that constant times the expectation of the function? Again, that's just taking the constant out of an integral, right? Because the expectation is an integral. And what about the variance of a constant times function? Well, that integral has things squared in it. So when you take the constant out of, I wonder if I have either of the things left. No, I just erased them all. Well, I mean, here's one of the things, right? If you had c in front of all of these things, or c times f of x, then each of these terms would have a c squared in front of it. And you'd factor out the c squared out of all the terms, and you would get c squared. Variance of f of x. Okay, so if we use this property, this is an aside, then the expected value of g of all these trials is 1 over n times the sum j equals 1 to n. And now, using the expectation of a sum is the sum of the expectations, which I just proved for continuous variables, I can say this is the sum of the expectation of g of xi. Right? Now, this sum is really just n times the expected value of g of x, right? Because these are just names for the different trials. And the experiment is really the same each time. So this n cancels that n, and the answer is the expectation of g of x. Right? So if you flip one fair coin, the chances are half that you're going to get the 1 point, say, and half that you get 0. So the expectation is a half. And that's also the expectation of the average. So all it says is the average is an estimator of the original expectation, the average of the results of the trials, because its expected value is the same as the expected value of one trial. What does that gain us? Why flip a coin 100 times then if you want to determine whether it's fair or not? Because there's a lot of variance, right? It's going to be either 0 or 1, which means the variance is always going to be, say, if it were a fair coin, the variance would also always be a half squared, because the difference. But the difference between this average and a half, if it's a fair coin, is going to be much smaller. If you flip it enough times, that difference would become significant, and you could tell whether it was a fair coin or not. So what I want to show is repeated trials decrease the variance. And so for that, I'm going to use the formula for the variance of the sum. So the variance of g of x is the variance of 1 over n times the sum j equals 1 to n of this g of xj. And that's equal, by the factoring thing I proved on this board, I have a 1 over n squared as the constant that's coming out, right? Because whatever that constant c was, when I can compute the variance, I get the c squared, because all these terms for the variance have squares in them. And then I have the variance of the sum and now I said these were independent experiments. Really, it's the same experiment where if you do it again, you're not messing up the results by what you got the first time. The second trial of the experiment is independent. So if you're generating random number generators to get your xj's, you better make sure that each time you get a new random number, it's not correlated with the previous one, or you won't be simulating the experiment well on a computer. So that's the reason people struggle so long to get high-quality random number generators. But I was just reading in IEEE Spectrum, they had a picture on the cover. I haven't read the article of using actual physical processes in certain newer chips to give you your random number generator, so they really don't depend on arithmetic. So since they're independent, the variance of the sum is the sum of the variances. I think I was j equals 1 to n. And since it's really all the same experiment, it's just the variance of this g of x. And like before, I have this is just n times the variance of each experiment. So to get from here to here, I used the fact that the experiments were independent. And now the n's don't completely cancel. I still have 1 over n in the denominator. So in a sense, and if I think of this as sigma squared for g, and this as sigma squared for lowercase g, then I can say sigma for the average is 1 over the square root of n times sigma for one trial. Right, so if I have a certain error for flipping a coin, say once, that would be, say, a quarter, I guess, is the variance, and the standard deviation is a half, because it's either 1 or 0 for my count of whether I got ahead or not. So my variance is always a half. I'm sorry, the variance is a quarter. The standard deviation is a half. If I flip it 4 times, I can make it a quarter. If I flip it 16 times, I could decrease by another factor of 2. So say you want to get your error to be 100 times smaller. You have to try 10,000 times as many trials, because it's the square root of that 10,000 that's going to give you the 100. Okay, so I just finished that one. Okay, now let's talk about Monte-Carlo integration, which is really the application in this course. So I might not finish it, but I can start. So what we're trying to estimate is an integral. Say the integral from a to b of f of x dx. And we make an estimate this is only going to be one sample. This is the integral, and the estimate is with one sample, f of x1 over p of x1. So you choose x1 from some probability distribution. It could be a uniform distribution over the interval from a to b. It could be a Gaussian. It could be anything. But you divide by the probability, because if you want to estimate f and you have a low chance of picking that value, you have to weight it by 1 over that chance to compensate. And so I'm going to call this a function h of x1. Maybe I should have used g. Then the expectation of this estimate, I1, is the integral from a to b of h of x, p of x, dx. And this is the integral from a to b of f of x over p of x times p of x dx, which is just the integral from a to b of f of x dx, because the p's cancel. Right? I was saying you want to weight inversely by the probability if you're not choosing all the points x equally, and that's your integral. So the expectation of this one sample is the integral. But it's like that heads and tails when the true value is a half, the very, very high variance. Because we only picked one sample, the expected value is correct, but say it was the average value for anti-aliasing of the color in a pixel, where the polygon edge went right through the pixel and half of it was black and half of it was white. It's exactly that heads-tails situation. Your variance is always going to be a quarter, and your standard deviation is always going to be a half. What you want to do is pick a lot of samples and then take the average. So we're going to do exactly what we did here. Maybe I'll start on this board. So let I of n be the estimate when you take the average over n trials of doing f of xj over p of xj. So now you choose n random numbers. In our case, they're one-dimensional, so they're just floats, single numbers. And you take the average of the values you get f as over p of x. Well, by what I showed on this board, the expectation is still the same answer, right? Because it's just the sum of those expectations. So the expectation of this new estimator for that integral is still the original integral. But now the variance of this, it should have been capital N, estimate is 1 over n times the variance of one estimate. I probably should have computed that, but that's 1 over n times the integral from minus infinity to infinity of f of x over p of x minus the true integral, which is the expected value, squared times p of x dx. Right? That's what this one of the things was. And so the same thing is true that I had the last time. The variance, the standard deviation of this estimate in equals 1 over the square root of n times the standard deviation, which is of one estimate, which is the square root of this integral of I1. Which means you can make your error as small as you want by doing enough trials. In fact, what I'll show next time is this Chebychev inequality, which says you can actually make the probability of the error between this estimate and the true integral being bigger than some small number, also as small as you like, by choosing n big enough, which is a more practical way of determining how many samples you need if you want to say, well, the probability that I'll be off by more than 1% is less than 0.5% or some deal like that. So I'll prove that one next time. The statement is in the book, but the proof isn't, and being trained as a mathematician, I always like to see proofs. So I did, except for that, I'm caught up.